Okay, so we start with our second lecture. We have our lecturer Argyres.
Yes, Argyres, Argyres.
From Cincinnati University. You are visiting Bariloche for 1 year.
Yeah.
So if you want to give us an introduction to yourself.
Yeah, my name's Philip Argyres. I've worked on supersymmetry for decades now. And I thought I would try to give an overview of n equals 2 supersymmetry in 4 dimensions. And in some sense, there's nothing too special about n equals 2 in 4 dimensions. I could have done it in other dimensions with different amounts of supersymmetries. And many of the techniques I'm going to try to review would still apply. But things are nicest in 4 dimensions, partly because we have a large class of Lagrangian, of gauge theories that have weak coupling limits. And so we have very strong tools to learn a lot about these theories. With n equals 2 supersymmetry, these are just field theories with a large amount of symmetry, which makes them easier to say precise things about them, but they are less realistic. People have some speculative ideas how extended supersymmetric theories may have something to do with beyond the standard model physics, but these are extremely speculative ideas. There's no evidence at all that they have anything to do with the real world. And that's not why I'm studying them. I'm studying them as a way of understanding strongly coupled quantum systems. So I'm pretending I'm more like a condensed matter physicist than a high energy physicist. So my plan is to very rapidly talk about the main ingredients, in some sense technical ingredients that come from supersymmetry, that aid us in analyzing these theories. And then probably in the next lecture, I will concentrate on 2 particular applications. One, the geometry of certain subspaces of the moduli space. This understanding of the geometry of the Coulomb branches is very much along the lines of what's called Seiberg-Witten theory. And then this notion of twisting, sometimes called topological twisting, though their twists are not always topological. And and this also is related to the applications of Seiberg and Witten to the topology and differential geometry of 4 manifolds. But I'd like to try to highlight a different application where, for superconformal field theories, we understand via a twist a different protected sector known as a vertex operator algebra, which has been very important in the last 10 years or so. And then I'll talk about many open problems. So that's my plan. Please interrupt me with questions. Okay. So, like I said, I'm going to try to go pretty rapidly over the basics. There's no way I can, teach you the basics in real time here. There's a whole formalism involved. First of all, what are supersymmetric theories? They are ordinary quantum field theories you can think of them as scalars, spinors, gauge bosons, and I'll just work in flat Minkowski space-time with some algebra of operators. I can choose a Hermitian basis, if you like, for these operators. And it's called, so this symmetry algebra is called supersymmetry if it has fermionic generators, which I'll call Q and Q twiddle, which close, by their anti-commutation relations, close on translations. So here, alpha, alpha dot are the usual Lorentz indices, the left-moving Weil spinor indices, right-moving Weil spinor indices. And this other index, capital I, J, those run from 1 to 2. Those are they're basically saying I just have 2 copies of this symmetry, and that's where this n equals 2 comes from. It's called extended supersymmetry. And so basically, the left and right moving supercharges, their anti-commutator closes on translations, and then otherwise everything commutes or anti-commutes, though there's this possibility of having something called a central charge, a scalar, a complex scalar conserved charge in the super Poincaré algebra, which ends up playing an important role, but I won't be emphasizing it too much. And then, of course, this is the space-time symmetry algebra of these theories. It has the Lorentz group, or in this case, I'm just showing the translations, and it has this fermionic extension of it. And then, of course, I can have the usual internal global symmetries, which I'll often call flavor symmetries. So I'm interested in understanding field theories with this symmetry algebra. And I've written the n equals 2 version. There's n equals 1, 2, 3, 4, any integer you like. Something you hear about is something called an R symmetry. It's an internal global symmetry under which the supercharges are charged. So in particular, in this case, there could be a U2 global symmetry under which where the I and J indices are the doublet of the U2. So in other words, the Q's and the Q twiddles transform as doublets under this symmetry. This is not part of the symmetry algebra. That is to say, a given field theory may or may not have this symmetry as an additional symmetry. Okay? It's part of it's what would be called the automorphism group of this algebra, but it's not necessarily a symmetry of a given field theory. Okay, so that's this is what people call super Poincaré algebra. And now there's a different extension, here we go, which is the superconformal algebra. Instead of having the Poincaré group, which is the translations and the rotations, the Lorentz transformations, there is the conformal generalization of this, where in addition, you have dilatations, the generator of scale transformations acting on space-time, and special conformal transformations, which are kind of inversions through the origin, together with translations, together with an inversion back. Those are generated by these Ks. So that algebra, P, D, M, K, that's the conformal algebra in 4 dimensions. And the supersymmetric extension has the supergenerators, and then also there's their conformal partners called the superconformal spinors. And the interesting thing to comment about this is this thing closes as an algebra on some scalar generators, namely those U2R generators that I mentioned before. Now, once you have a superconformal symmetry, these are part of the symmetry algebra. The theory has this as a symmetry. There's not an option of leaving these guys out. In particular, the QS commutators close on these generators. So I haven't it would take a page to write out all the commutation and anti-commutation relations. I'm not going to bother to do it. And I think let's just ignore this for the moment. But one thing to comment is that the superconformal algebras are simple Lie superalgebras. There are no the associativity, the graded Jacobi identity fixes all the coefficients, up to some scalings, arbitrary scalings of this algebra. So these are very rigid algebras, and there's a full set of these that are known. There's just a finite set of possible superconformal algebras in dimensions 3, 4, 5, and 6. They don't exist in dimension 7 and higher. Okay, so a theory that has n equals 2, say, superconformal invariance in 4 dimensions is an extremely rigid field theory. It has a huge amount of symmetry, and we've made enormous progress over the last quarter century in solving it, in computing observables, a certain set of observables in these theories exactly. So that's what I want.
Yeah.
Yeah.
In this case, n is bounded by 4, or?
Yeah, and goes up to 4 if you want superconformal symmetry. For super Poincare symmetry, n could be anything that you liked. Once n got above 4, though, the smallest free particle multiplet included spins above 1. And the only consistent theories we know that have spins above 1 involve gravity. So if you wanted a non-gravitational theory, you needed to stick to n less than or equal to 4 in 4 dimensions. I don't seem to be able to. Here we go. I don't know exactly where to point. So once you have a symmetry algebra, the first thing you do is try to figure out its representations. I'll go very rapidly through this, but let's remember for Poincare algebra, the representations are the state or the particle representations. And the idea is you look at eigenvalues of the translation of the momenta. You go to a state which is an eigenvalue of the momentum, and also you can choose it to be in a given representation, if you like, of the rotations of the little group preserved by that momenta. And those describe the particle representations of the Poincare group that you're familiar with from your quantum field theory course. Once you have supersymmetry, we have these other generators, these supercharges, so we just take those representations and act on them with the supercharges. And there's only a finite number of states, of new states I can make this way, because this subscript here is the spinor index. If I hit it with 2 Q1s, I get 0, because Q1 squared vanishes by the commutation relations. And similarly for Q2 and so forth. So the net result, if you just check it up, if you just do the numbers, it's 2 times 2 times 2 times 2 times 2 times 2, 4 times 4. I'm sorry. I see. For n equals 1, I would get 16 possible states. For n equals 2, there's also another index, the other index. So then I get 16 squared, 256 states. So the multiplets are these states. And you can see that if the first state was a boson, hitting it once with a Q would make it a fermion, twice a boson, and so forth. So you have equal numbers of bosonic and fermionic partners in these multiplets. And they're generally called super multiplets. Okay. And so there's many of these multiplets that you can write down. And if you're interested in massless states, and those are the ones that we're going to be concentrating on, we can describe them by massless free fields. And like I said, let's restrict ourselves to spins less than or equal to 1. Then with n equals 2 supersymmetry, there's only two representations called the hypermultiplet, which has spin 0 and spin 1/2, or the vector multiplet, which has spin 0, spin 1/2, and spin 1. The other ones all go up to higher spins. And so the key thing here is the hypermultiplet. What we'll focus on, it has 2 squarks, as people would like to say, 2 complex scalars. They form a doublet under the SU2R. And whereas the vector multiplet has a vector boson, and it also has a single complex scalar superpartner. And of course, there's the fermions that go along for the role. If you look at this and count the degrees of freedom, these have 4 bosons and 4 fermions, or 8 bosons and 8 fermions, much less than the 256. So these are called short or BPS multiplets. They have states which some of the Q's acting on these states annihilate them. Okay, and that's these short or BPS multiplets. They're also called supersymmetric multiplets or protected multiplets. These will play a key role. It's observables involving these fields, which are the ones that will be able to compute exactly in these theories. Okay, so that's an indication of the representation theory for the super Poincare algebra. For the super conformal algebra, the representation theory is much tighter in some sense, because as usual in conformal field theories, there's a state operator correspondence. I won't go into it too much, but if you do one way of thinking about it is if you do a Wick rotation to Euclidean signature and then you can do radial quantization and use the dilatations to take any state and shrink it down to a point. And so you can make a correspondence in that way between a local operator insertion and any state in your Hilbert space. And so I can describe my representations by some local field with some quantum numbers, which just tell me the quantum numbers of the Lorentz, the Lorentz spins, the scaling dimension, and the R charges. And for each of these choices, this gives me some field representation, and it's called a superprimary, and it has the property that it's annihilated by the superconformal charges. And so you start with that superprimary and you just act on it with the supercharges, the Qs. They kind of act like raising operators. And just as before, there's only a finite number of them because of the nilpotency of these guys that fills out the supermultiplet. Yeah, there is. There's in Minkowski signature, you can go to the conformal compactification of spacetime, and by conformal symmetry, the theory and its correlation functions are well defined, and the conformal the universal cover of the conformal compactification of Minkowski spacetime in 4 dimensions is S3 cross time. So it's like a cylinder, and there the usual time quantization would be taking slices, which are these S3s, and then and instead of doing dilatations, you just use the time translation generator, your usual Hamiltonian, to push your state arbitrarily far back into the past. So it ends up giving the same result. Okay. And so, for certain relations among these quantum numbers, which I'll mention in just a second, then you have these short multiplets, these protected multiplets. And this has all been worked out. And there's this beautiful paper by Cordova, Dumitrescu, and Intrigligator from 10 years ago, in which they simply work out in a very logical and organized way all the different multiplets of all the extended supersymmetries and all the dimensions, and has a logical naming scheme. It's a wonderful reference if you want to work in this game. So some consequences of this algebraic structure. In conformal field theories, we have unitarity bounds. If it's a unitary conformal field theory, an honest to goodness quantum field theory, then there are restrictions on what the scaling dimensions and the quantum numbers of the fields can be. So without supersymmetry, you know that there's a unique field with dimension 0, that's just the identity operator, and the corresponding state is the ground state. And then everything has dimensions 1 or greater. And when they saturate 1, let's say that they have spin 0, so the J's and J twiddle are 0, then that's saying that the lowest dimension scalar field has dimension 1 in a unitary theory. And of course, that's the free scalar, free massless scalar in 1 dimension, and so forth. So there's a super analog of this. It's a bit more complicated, but you get similar sets of inequalities based on the quantum numbers of the fields. Again, you should look here for the full explanation. But when these inequalities are saturated is when you tend to have these supersymmetry protected states. Yeah.
You have big R and little r. One is SU2, the other one.
Yeah. One is the Dinkin index of the SU2 index. So if you were thinking about like an isospin of the representation, that's what big R is. And little r is the U1 charge.
So the asymmetry is always U2, not SU2.
It's U2 for n equals 2. It's UN for n 1, 2, and 3, and it's SUN for n equals 4, and then it stops. Okay, I mean, there's a whole classification of simple Lie superalgebras due to, I think, Katz, the mathematician Katz, from the 70s or something like this. But it's similarly complicated to the classification of simple, regular simple Lie algebras. So I'm just quoting it.
My question was whether when people say that the BTS bound, whether it is associated with the SU2 or with the SU1, where the dilatation. You can have both.
You can have both, and they're different kinds of short multiplets depending on them.
They would be way the same kind of short multiplet.
No, they're kind of different. If I don't know if you're familiar with this, so the typical physics that's going to happen in gauge theories is going to be the Higgs mechanism, where these scalars that I mentioned in the hypermultiplet or the vector multiplet get vacuum expectation values. And if it's the scalar in the vector multiplet that gets the expectation value, that's called a Coulomb branch direction of the moduli space, and those correspond to BPS multiplets with non-zero U1R charge but zero SU2R charge, and vice versa for the Higgs branch. Okay, good. So I'll talk a little bit more about this. Well, quite a bit more about this later on. But oops, that's not what I meant to do. Well, here, let me go back one more. Here is our super Poincaré algebra, not the super conformal algebra, and I mentioned that there can be these central charges, which I called Z here, and there we go. A consequence of that algebraic structure is that, and this is purely just from the algebra, is that this Casimir, what we would call the mass squared of the state, is bounded below by the absolute value of that central charge, eigenvalue. So this was pointed out long, long ago by Witten and Olive, it turns out that the central charges. What does central mean? Central means as a generator, it commutes with all the other generators in your algebra. So it's like an internal symmetry charge. In the cases that we'll be interested in, it corresponds to some global quark number charges, and they can also correspond in theories in which you have a low energy free electromagnetism. It can be linear combinations of the electric and magnetic charges under those low energy U1s of the theory. And so it tells you that in these charge sectors, there's a bound. In these supersymmetric theories, the mass of particles have to be greater than this bound that's just given in terms of conserved charges. And when it's saturated, and I think this is what you were referring to, then you have these what are often called BPS particle states. I'm not going to say too much more about this, but I just want to bring it up because these BPS bounds are sort of play a very important role, and I'm just kind of sweeping them under the rug here, but they're sort of behind a lot of statements that I'm about to make. If I can There we go. One basic thing you can do is apply this bound to the vacuum state. So the vacuum state is supersymmetric if and only if it's, so there's no spontaneous breaking of supersymmetry if and only if the vacuum is annihilated by all the supercharges. And if it's annihilated by all the supercharges, then by the algebra, then it has, of course, 0 momentum, which you'd expect of a vacuum state, and also has 0 central charges. And the contrapositive of this is that supersymmetry is spontaneously broken if and only if it's not annihilated by the 4 momentum. In particular, I can allow it to have a positive energy, but still 0 momentum. We don't want to break translation invariance or rotational invariance. So in these supersymmetric theories, supersymmetry is spontaneously broken if and only if the vacuum energy is above 0. Usually there's no normalization in these non-gravitational theories to what we mean by the 0 of our energy, but we have implicitly a built-in normalization once we have a supersymmetry algebra. Maybe I can just go back and point this out. Here we go. I can't, for this algebra to make sense, I can't offset this by a constant anymore. So I've chosen a normalization of my zeros of my energies by writing my supersymmetry algebra in this way. And the statement is this supersymmetry is spontaneously broken if and only if the lowest energy state has a non-zero value for the energy in this normalization. Okay.
So the sign is not that important, that it's not 0.
Well, it still satisfies the BPS bound, and Z is 0. So the mass, the energy eigenvalue will be positive. Oops, sorry. Okay, somehow I.
Maybe you should come to the
Much more reliable. Okay, the last thing I want to say, and I'll try to do this quickly, we'll come back to it later, is the other thing, in addition to these sort of selection rules and on quantum numbers, there are also ward identities. And a typical ward identity that you would say from a symmetry is if I have a symmetry generator, I just I insert that symmetry generator in a correlation function, say next to the vacuum. My correlation function is a vacuum expectation values of a bunch of insertions of, say, local operators. And if I insert my symmetry generator next to the vacuum, it annihilates the vacuum. I'm assuming that the symmetry is not spontaneously broken. And now I can commute the symmetry generator through to the right, and then until it hits the vacuum on the other side and annihilates it. And the result is I get a sum of terms with the symmetry generator acting on each individual field and equal to 0. And that's the typical symmetry ward identity. Exactly the same thing works for supersymmetry. The interesting thing here is every time my super charge acts on a given field, it changes it from a boson to a fermion. So I have some sort of identities that a sum of correlators with a bunch of sequential fermionic insertions sums to 0. That's the typical thing. But there's some more interesting ward identities. This will seem a little cooked up, but it will come back when we talk. No, I'm pointing with the pointer, not. It will come back when we talk about topological twisting, and this will be key. Say that I have one supercharge, which I've written with this funny Q here, such that such that, and a bunch of fields which are BPS, are annihilated by this supercharge. They're in these short multiplets. And let's say this supercharge, in this particular example, happens to be such that I can write an arbitrary translation as a anti-commutator of that supercharge with some other supercharge, which I just called Q mu to give it a name. This is actually, there does exist such a supercharge in n equals 2 supersymmetry. It's called the Donaldson-Witten supercharge. In any case, what would be the consequence of having this situation? Well, let's say I tried to make a correlation function of these short operators, and they're all at inserted at different points in space-time, and let me take the derivative with respect to the insertion point of one of them. Let's say the first one, it doesn't matter. Of course, the derivative acting inside on phi, that's just given by the commutator of the translations with phi, but the translations can be given as this anti-commutator, and then by the Jacobi identity, or the graded Jacobi identity, I can rewrite this as this Q mu acting on the commutator of this double struct Q acting on phi, plus the vice versa. So phi was annihilated by it, so this first term goes away. The second term has Q mu acting on phi, that's some fermion, and it has this double struct Q on the outside. And now I can play the game of taking this Q. If it acts to the left, it annihilates the vacuum. If it acts to the right, I just keep on commuting it through. And so I get Q's acting on all of these terms, but Q's acting on all of those terms gives me 0. So at the end of the day, when the dust settles, I get identically 0. What I've learned is that this correlation function doesn't depend on the position that I inserted this operator. It's completely translationally invariant. We would say it's a topological correlator because it doesn't care where I put the insertions. I applied this argument to the first insertion, but I could have done it to the second, the third, and so forth. Okay, this is how we're going to get how we're going to construct a rich class of topological field theories from what's called twisting of n equals 2 supersymmetries.
Sorry, Philip, these are what are called the chiral.
Yeah, in this case, these would be chiral superfields, yeah. They're not the interesting ones in Donaldson-Witten theory, where you have instead chiral line operators, but we'll get to that. Okay? So this was a lightning review of just to give you a flavor of what are the basic symmetry-related consequences of having supersymmetry or superconformal invariance in a field theory. So next I want to talk about Lagrangian supersymmetric field theories. And as I said before, what I'm going to focus on are non-gravitational. And furthermore, I'm going to talk about local quantum field theories, which are UV complete. So I'm thinking that I have a local quantum field theory, which is a UV fixed point plus some relevant deformation, and it flows, and in the infrared, it's some infrared fixed point theory. We know there are many counterexamples to these things. We know now of theories of theories which we realize by effective field theories and RG flows, and we know that there is no UV completion of them, that you have to complete them by a gravitational theory or by stranger things, string theories. These so-called little string theories are examples of these things. So this is an assumption, but it's just this is often what we kind of think about as our kind of these very nice sort of self-consistent, complete local field theories. And maybe for simplicity, this is the best studied class of theories. But I'm just pointing out it's by no means the most general class of things that we might want to call field theories. And what's a Lagrangian field theory? I just mean one where the ultraviolet fixed point is free. That means that as you turn off whatever like relevant deformation that you turned on to start the flow away, it becomes a free theory. Asymptotically free Yang-Mills theories are examples then of Lagrangian theories. All our machinery in terms of path integrals and perturbation theory all assume that we start at a free theory and then we do perturbations or modifications around it. Okay.
Sorry, Philip,
Yeah.
on general grounds.
Yeah.
So when you say what features would make an infrared theory not to be complete?
No, I don't know the answer to that question. This is a kind of a swampland question, saying, can I point to a set of properties that infrared fixed points have to have that make it impossible for them to have? In this case, I'm not asking for a string theory completion, but a local quantum field theory completion. I don't think the answer to that question is no. We have a certain set of counterexamples, especially in 5 and 6 dimensions, via string constructions. These so-called little string theories are examples.
You have examples, for example,
Yeah, I don't know too much about it, but I believe so, because I can take these 5-dimensional and 6-dimensional counterexamples and just compactify them on circles and preserving the supersymmetry. So I'm pretty sure that they also exist in 4 dimensions. I mean, and we also know many things. An example that's going to play an important role is where the infrared conformal field theory is just free, an abelian gauge theory, free U1, electromagnetism, let's say with massless charged matter. So it flows to an infrared free theory, and we believe there is no UV completion without adding new massive degrees of freedom in order to get it to flow to a UV fixed point. Anyway. Okay, so the next step is just to start to talk about free massless, the theory of free massless hypers and vectors before turning on, trying to figure out the relevant deformations so we can think about them as UV theories, or the irrelevant deformations, thinking of them as flowing into these theories, perhaps in the infrared. So this theory is very simple. It's a theory of electricity and magnetism for the vector multiplets together with the hypermultiplets, and if they're free, it means nothing's interacting, nothing's charged under the U1s. So it's a bunch of neutral scalars and spinors. That's it. So it's a free theory, so you'd say there's not much to say to it. And one thing, though, that needs to be pointed out is that even in free electromagnetism, there's an ambiguity in our description of these theories, which is called electric-magnetic duality. It says that I can write things down that look like they have different, I write down what look like different Lagrangians, and they're actually the same free theory that we're talking about. So I'm just going to remind you and introduce some notation because this ambiguity plays a big role. So I write the Lagrangian for electricity and magnetism, forget supersymmetries. This just has electric and magnetic fields. I'll write it in this funny way, F mu nu squared, but this is a script F, which is the self-dual part of F. So F plus the Hodge dual, where you interchange electric and magnetic fields, and in Minkowski signature, you need to put an I in there for it to be self-dual. And that's why, so this thing is complex, and I'm taking the imaginary part. I don't know, it's just some choice to write the Lagrangian. And this is just a number out front, which in the usual way of writing it, you would think of like 1 over g squared as a coupling. So by taking the imaginary part here, it's the imaginary part of this number, which is this coupling. And then it turns out by packaging it in this way, the real part of this number would be the topological term, the theta angle. We want this coupling to g squared to be positive for unitarity, or in this way of writing things, the imaginary part of this complex combination of couplings to be positive. So this is just a way of packaging traditional electromagnetism. And here is this set of invariances of this theory. One of these electromagnetism theories with fields F and coupling tau is equivalent to the thing with a different field and a different coupling. So I'm changing the coupling. So this isn't a symmetry. This is more like a gauge invariance, if you like. If the coupling tau prime is related to the first coupling by this fractional linear transformation, where A, B, C, and D are integers, are an integer determinant 1 matrix. Okay? And at the same time, I change the, if you like, the electric and magnetic, the F and Hodge dual F, they transform as a 2-component vector under this change of basis. So this is actually, these kind of rotations of the electric into the magnetic field is just the traditional sort of a version of the classical ambiguity between what you decide to call electric and magnetic in an otherwise free theory. If you didn't have any sources in the theory, you wouldn't know what to call. But of course, it's a free theory, so what is this coupling constant even doing there? It's arbitrary as well. So what this really means is I'm thinking of the electromagnetism as a low energy effective theory, and there are some charges in the theory. They're all massive charges. So I'm thinking that I have a whole set of massive electric and magnetic charges in my theory. And then tau, the 1 over g squared, its imaginary part, has to do with the strength of the coupling of my photons to these massive, say, non-dynamical sources in the effective theory. So that's actually the framework in which you make sense of this electric-magnetic duality transformation. And so I put my electric and magnetic charges together in a 2-component vector. So they form some lattice, which we call the charge lattice. And they're not arbitrary values of these charges. They have to satisfy that a certain antisymmetric pairing between these charges has to be an integer. And that's the direct quantization condition. And so you normalize things so that these electric, magnetic, and electric charges are themselves integers. And then you see that this electric-magnetic duality invariance is this group of invariances are just actually the group of possible basis changes of the charge lattice that preserve the Dirac pairing. The Dirac pairing, it doesn't have a better name, sometimes it's called the Schwinger-Dirac pairing, is actually a physical observable. What it measures, if you have two charged heavy sources, static sources, hold them fixed at some large separation, you can measure the angular momentum in the electromagnetic field that they source. And that angular momentum in units of h bar over 2 is this integer that's Dirac pairing. So it's something that you can experimentally measure. Okay, and then I'm just going to briefly mention the generalization to if you have many copies of electromagnetism. The number of copies of electromagnetism I'm going to call the rank of the theory. So the rank is going to appear a lot. And now we have electric and magnetic charges for each U1. So now I have this rank 2R lattice with a big Dirac, kind of symplectic Dirac pairing, which can be given by this kind of symplectic pairing. Okay? And then the generalization of electric-magnetic duality is the analog of the group of basis changes of lattices which preserve this pairing, which is this integer simplex group of 2R by 2R symplectic matrices. So this is the generalization of electric-magnetic duality. These are going to play key roles in what follows. The other thing to notice is when there was one, when it was rank 1, so there was just one coupling, it was just tau, but now we have field strengths for each different U1. And so there's a symmetric complex matrix of couplings. And so the effective matrix is this complex matrix. Its imaginary part as a matrix has to be positive definite. It's the matrix of couplings. And the real part are sort of a matrix of theta angles. And maybe one other thing I should say, in case you haven't seen this before, is generally in the quantum field theory courses, the theta angles are discarded for U1 factors, and they're said to only give something interesting in the non-abelian factors. But if you have both electrically and magnetically charged sources in abelian factors, then the theta angle has observable consequences. So the theta angle is important, even in electromagnetism, if you've got magnetic charges in the game, as well as electric charges. Okay, so how am I doing on time here? Oh, okay, good. I think...
Is little r related to the little r?
No, sorry. Very good. Before little r was a U1R charge, and this one is just an integer, which tells me how many copies of electromagnetism I have, which is the rank. I think from here on out, little r is the rank. Sorry about that. So far, actually, everything I've said has nothing to do with supersymmetry. It's just electromagnetism. Now I want to make not just U1 vector plain old electromagnetism, but now I want to put them in these n equals 2 vector multiplets. Then basically I have the same structure. Here are the gauge pieces, and here are their accompanying complex scalars, which I'll just call A, one for each multiplet. And they have a very, and then I'm just telling you that n equals 2 supersymmetry says that this is the way they come in together. And there's also, of course, fermionic partners, and I'm not even bothering to write them, but they also, all their couplings are fixed in the free theory in the same way. There are scalars. These are scalars in, if you like, in the adjoint representation of U1, which just means that they're neutral. They don't carry any electric or magnetic charge. So it's perfectly okay, if forgetting supersymmetry, to write down a potential term for these guys. That doesn't violate gauge invariance. However, supersymmetry forbids the potential term. There's the super partners of this potential term would be non-gauge invariant terms because they include the vector multiplets. And so the only things you can write down are these free massless kind of kinetic terms and no potential terms. No mass terms are allowed. Okay? So if you thought of this as a theory, it actually doesn't have a unique vacuum. I can take it, which is the state in which, you know, the fields are all zero. I could shift the scalars by any constant complex amount, right? As long as they were constant in space-time, I'm not changing the energy. So this is another vacuum of my theory. So I have a whole moduli space, a whole continuous space of vacua of this theory. Of course, it's a free theory, so this isn't too, this doesn't seem very special, but the whole point is this moduli space of vacua is going to persist even after we turn on interactions. So it's a complex space, one complex direction for every U1 multiplet. So the rank of my theory is also going to be the complex dimension of this moduli space of vacua. Here's my picture of the moduli space of vacua. Actually, I should point, there's an origin where there's 0, where, well, okay, whatever. Anyway, so thinking of this as a low energy effective theory, I wrote in the previous slide here tau ij as if it's just a matrix of constants, but it's perfectly consistent with supersymmetry for tau ij to vary as the values of A vary. So this, a slight generalization of these things, which are still infrared free for every given vacuum, for every given point in this moduli space. The tau ij's just are fixed at some constant value and it's a free theory there, is this kind of supersymmetric version of a nonlinear sigma model, where this coupling tau ij varies as I allow the expectation values of my scalars to vary. So now, and I'm just going to tell you that by demanding supersymmetry, invariance of my Lagrangian, if I allowed tau to depend both on A and its complex conjugate, then I find that there's a term in the supersymmetry variation that depends on the derivative of tau with respect to the A bars, that's multiplied by a term that cannot be produced by any other supersymmetry variation. There's not another term that I could write down whose supersymmetry variation would cancel this. So these terms are disallowed by supersymmetry. And in particular, what that means is that tau can be a function of the A's, but not the A bars. Taus can only be a holomorphic function of the expectation values of the scalars in the vector multiplier. So, okay, that's very fast. It's the kind of one of the a very technical supersymmetry derived selection rule, but it has this important result. So the result is that what before I was just thinking of as a vector space of values of A now gets a whole geometry. It inherits the geometry. If you look here, in the usual way of a nonlinear sigma model, the coefficients of the kinetic term, which in this case is the imaginary part of tau ij, acts like a metric on the space of vacuum expectation values of the field. Yeah.
The statement before that potentials are not allowed by supersymmetry doesn't. You're not including interactions from tau dependent.
Yeah. This is an independent and correct statement that the potential terms, the no derivative terms, are not allowed. But these non-polynomial terms that have two derivatives are allowed.
So the fact of these states, they fields being complex, they are complex.
Yeah.
So you don't have a state symmetry or so possibility. You're not.
In some examples, there is a phase symmetry on the A's.
Would not allow this tau to depend on A?
Actually, we'll see examples, and in the simplest examples, where you just have rank 1 and there's a single field with this phase symmetry, tau is indeed independent of A. But there are many more complicated examples with many A fields, and then the symmetry isn't under an individual phase rotation of 1A, but collectively of all of them, and then you can still have very complicated tau dependence.
Sorry, I think I'm making the same question as Nicolas. Suppose I make PHA depending, or I would like it to be dependent on A and A bar.
Then I'm claiming that any such effective theory violates n equals 2 supersymmetry.
Ah, okay.
That's what I was trying to encode here. I know this is way too cryptic, but The idea being that if I had such a term, the supersymmetry variation would be non-zero. And there's no other way that I can modify this Lagrangian to cancel that supersymmetry variation.
Sorry, what broke the symmetry between A and A bar?
Excellent question. It's not so much that the symmetry is broken. There is a symmetry between replacing A's everywhere with A bars. What's happened is that the self-dual half of the vector potential is being connected with the A's, and the anti-self-dual with the A bars. And there's an overall symmetry in which I just replace A by A's bars and self-dual by anti-self-dual. And of course, and also the fermions go in there. You have the left-handed, Weyl fermions and the right-handed Weyl fermions. They're also coupled all together with the. I don't know. Does that answer your question? Okay.
Sorry, but you can make tau only dependent on A.
Yeah.
And then how I don't get in trouble when I try to do a supersymmetric transformation? That would get me something that depends on vector field, but then don't I break gauge symmetry? I have an explicit dependent on U, or do they enter in a way that?
Well, the gauge symmetry is preserved here. I've written, what I'm claiming for you is I've written down a Lagrangian, an infrared-free Lagrangian, which is manifestly gauge invariant because I've just written it in terms of field strength, and I claim it preserves n equals 2 supersymmetry. So you're just asking about the mechanics of how do I see, now I do a supersymmetry transformation on this, and let's say acting on one of the fermion terms, I might generate something which is gauge variant, but the answer is no, you'll never do that. Yeah, the gauge variations of the fermions will close on the F's, not on the A mus. Okay. Okay. So now we have this idea that when we have these free infrared free vector multiplets, we will have a whole moduli space of vacua where the vector multiplet scalars can get vacuum expectation values, but it can be a complicated geometry with this metric, the imaginary part of tau ij is a metric. It's actually a Hermitian metric, and so this becomes a complex Kähler space. And furthermore, and I'm not giving you any details, there's a further selection rule on the properties of tau ij, which says that this combination of mixed derivatives is sometimes called the special Kähler integrability condition is satisfied. And when you have such a complex geometry with this condition, it's called a special Kähler manifold. It's a certain tightly constrained subset of complex Kähler geometries. You can run the same type of reasoning for hypermultiplets instead of for vector multiplets. There's no vector fields. There's only spinors and scalars. The scalars come in these pairs of complex fields, and they're actually best parametrized by just parametrizing them as components of a quaternion. And so their moduli spaces turn out to be hyper-Kähler manifolds. Okay? But unlike the special Kähler manifolds, the vector multiplet directions, there is a term allowed by n equals 2 supersymmetry, which is a mass term. And the mass term then lifts the flat directions. They're no longer possible vacua.
Sorry, so can I rephrase to see whether I understood or not?
Yeah.
So you say to me, I give you complex scalars, which will be in the same multiples as the vector. You write a kinetic term, but now the kinetic term, you mix I and J with some complex kind of nonlinear sigma model, and then you put the fermions necessary for distributable symmetry.
Yes.
And the claim is that had I tried to put the Tij depending on A and A bar, this is not
exactly. So I really what I'm doing is I'm classifying, I'm looking at a low energy derivative expansion, and I'm just classifying the terms order by order in derivatives that satisfy supersymmetry. And what I wrote here was with the holomorphic A dependence of tau ij are the the lowest order terms in such a derivative expansion that are allowed by the symmetry. So if supersymmetry is not broken, and I'm flowing and I have these flat directions, we need to make an argument that they exist, but in an interacting theory. But if I knew they exist, then the low energy effective action would look like this. Yep. I'm not putting in a potential energy term. There's no zero derivative terms lifting the energy of these spaces. All this nonlinear sigma model did was modify the kinetic terms. So locally, let's go back here. This is a great question. Locally, let this depend on A, but locally, let me look at a point where A is given some constant expectation value, then it's constant, so the derivative terms don't contribute anything. There's no, what I really should do is not look at the action, the Lagrangian. I should develop what the energy is. In other words, change the sign on the time derivatives. But because they're constant, and these are derivative terms, they just give zero contribution to the energy.
But a constant shift, constant A.
No, that's what I'm saying. If there was a potential, if I had a I don't know if you can see here. If I had a potential that depended on A bar, I need a real potential energy, then clearly if and this potential as a function of A did something like this, clearly if I shift A, then I'm raising the energy. But if I have this thing, if I shift A, this means everywhere in space, I shift the expectation value of A. I just add literally a space-time independent constant or spatially independent constant to A. The derivatives kill that constant term and do not change the energy. Oh, no. The moduli space are all constant A's. If I look at a field configuration with A spatially varying, then I get a contribution from the kinetic term. That's not a ground state, yes.
Sorry, but how do the Shukawas look like? Do they depend on derivatives of A? What is once you put tau depending on A?
Yeah. There's a derivative of A with two psi's.
Okay, so
yep.
it will be
yep.
invariant under the sheet.
Yep. Yes. The counting is one derivative is equal to two fermions in this low energy effective kind of supersymmetric counting of the derivative expansion. So I just by grading it in that way, you can actually see, without any work, so to speak, see that the Yukawas always have come with the derivative of the scalars. Okay, these are great questions. These are there we go. So now, again, how much? 10 minutes. 10 minutes, okay, I'll try to speed up. a little bit here. This is just standard stuff about Yang-Mills theories. If I have vector multiplets, how can I turn on, and now I'm thinking in the UV, what are some relevant interactions? Well, I can turn on a non-abelian gauge coupling, and that can be a relevant interaction as long as I don't have too much charge matter, light charge matter. I can couple hypermultiplets to vector multiplets, whether they're non-abelian or whether they're abelian, by letting them be charged under them, right? Or charges, I guess we call them charges if they're U1s, or transforming in representations of the non-abelian gauge group. And then, as I said, there are a very select set of supersymmetry preserving deformations for the hypermultiplets that you can think of basically as their masses. It's a slight generalization, but I won't go into it. And then, if I'm starting in a Lagrangian theory, so my UV description is free, then I can do perturbation theory, and I can ask, let's say at one loop, what's the one loop running? And then, so let's assume that we're turning on relevant generators, so these are asymptotically free theories. Here's the one loop result. It runs as a logarithm relative to some strong coupling scale, you know, the scale that you develop by dimensional transmutation. And it's very convenient to make it into a complex strong coupling scale where the phase has to do with the theta angle. And the rate of the running is just given by the coefficient of the one loop beta function. Here I've just quoted it. And once you put, in general, without supersymmetry, and then once you put in, you know, what fermions are in the vector multiplet and what ones, and how they're associated with scalars, it turns into this simple formula. It's just given by the index of the adjoint representation of whatever your gauge group is. That's kind of the contribution of the vector multiplet, and minus the sum of the indices of whatever representations the hypermultiplets are in. So as long as you don't put in too many light hypermultiplets, it stays asymptotically free. Okay, this is just standard one loop running. Now, we said that now we ask how this coupling runs with scale, becomes an effective coupling in the low energy theory. And we've a quick and dirty way of making the following argument is that this coupling running means it can depend on this strong coupling scale, but the strong coupling scale enters into the Lagrangian in the effective theory in exactly the same way as the lowest component of a vector multiplet. In other words, you can make it part of a, I forget what the name of this is, spurion field or something like this. Anyway, what that really means is that n equals 2 supersymmetry imposes a selection rule that tau can only depend on this complexified strong coupling scale holomorphically. So, and the theta angle periodicity tells me, if you remember, the real part was theta over 2 pi. It tells me that tau, under phase transformations of lambda, tau has to come back to itself by tau plus 1. So the only possible dependence of tau on lambda is in this combination B naught log lambda, which is precisely the contribution you got from one loop. But higher loop terms, which would involve log squareds, log cubes, and so forth, are not allowed by this selection rule. You can have power law things. If you look at those, these are the things that you would recognize, since they go as the strong coupling scale to a power, as instanton contributions. So you get this, this result in asymptotically free n equals 2 gauge theories, again, with the assumption of no spontaneous supersymmetry breaking, that that the running of the coupling, the beta function is one loop exact, but of course can get instanton corrections. And furthermore, if you look at this thing, if you arrange things, which you can certainly do just by picking these representations right, and it's a little group theoretic thing, to arrange the one loop beta function to vanish, then this term vanishes and these terms are constants. And so what you learn is that this coupling does not run at all. It's not traded for a strong coupling scale. It's an exactly dimensionless parameter in your theory. So this selection rule from n equals 2 supersymmetry gives me a large playground of gauge theories which are automatically scale invariant. There's no mass parameters. They have an exactly marginal gauge coupling, which I get to tune at will and will not run. Okay. These are them. You just take n equals 2 Yang-Mills theory, and you put in some matter, these hypermultiplet representations, such that you cancel the one loop beta function, and it becomes a superconformal field theory with an exactly marginal deformation. So instead of here I've tried to make this cartoon. This is the field theory space, and instead of there being one UV fixed point, there's a whole, in this case, kind of a complex manifold of UV fixed points labeled by different values of this coupling parameter. At one point, when tau goes to, I guess in this normalization, tau goes to I infinity, it's the free UV fixed point. But I can modify it to some, tau equals I, or tau equals, 3.2 or something like this, and I can, and then I have some interacting conformal field theory that's continuously connected to a free, a Lagrangian description. And then from each of these points, I can now take these hypermultiplets and turn on a mass parameter that's a relevant deformation and initiate an RG flow to some other theory in the infrared. And depending on where I start, I'll flow different places perhaps, and I'll get some set of infrared fixed points. This is kind of the problem that we want to solve. We have some class of now, in this case, of these Yang-Mills related ultraviolet fixed points, and we want to understand that if I turn on mass parameters, and there might be many mass parameters, so many possibilities, what's their fate in the infrared? What do they flow to? What's their what does their long distance physics become? So understanding the shape of this manifold of UV fixed points is called S-duality. And by the way, this purple manifold is called the conformal manifold. It's not a moduli space. It's the parameter space of conformal field theories here. And then answering this question of when you turn on different relevant operators, what's the infrared physics? That's the question of what's the phase diagram of the theory, or what's the RG flow of the theory? Much like these are the sorts of questions that you typically see in your condensed matter courses. And the point is, following this, the work in the case of SU2 Yang-Mills theories of Seiberg and Witten long time ago, I guess whatever this is, 30 years ago, using these techniques and these arguments, we've been able to answer these questions in a huge number of cases, in infinitely many cases, many different families. We now know the exact answers to these questions. So I don't know how much time I have left. It might be a good place to stop. Yeah, okay. Yeah.